right now, we are able to determine the mass of a particle if we know the composition, like how many carbons, hydrogens, fluorines, okay? If you know that, then voila, you can, tell me the molar mass of the compound or the relative mass of the particle. We can do that. But however, our life is not going to be as simple as that, I mean, when it comes to real stuff. Like, for example, if we get a sample from Mars or an asteroid or a comet, okay? So if we have an unknown particle, we do not have the composition. And how can we determine the mass of that particle? Okay? To do that, we're using a technique called mass spectrometry. So today, the main goal is to talk about learning objective. Main learning objective is to talk about mass spectrometry. Okay, so being able to solve something like this is going to be the learning objective today. Okay, and then I can assure you, anything that they send to like Mars or any other planet or a comet or an asteroid to, so they include mass spectrometry, mass spectrometry. Okay. So because, it's a very useful technique, it's a very powerful technique. Okay. Yeah, they're used really well in science. All right. Anyway, any questions, concerns, comments before we begin? Anything? I see a question already over there. Remind me your name, sir, one more time.
Evan.
Evan. Evan? Evan, go ahead.
Do you know if the questions can be reopened or after class?
Oh, yeah. So this is just to give you an idea about what we want to achieve by the end of today. This is the learning objective. Okay. I'm going to come back to this after, talking about the background. This is just to give you a preview of coming attractions. Okay. All right. So with that, I learned. Okay. I completed my move circle, which is great. So let's go back to the beginning. All right. So has anybody seen Cosmos? Can I see the hands? Who has seen Cosmos, the TV series Cosmos? Seriously? No? It's not animated, but it's not, yeah? So does anybody know who Neil deGrasse Tyson is? Okay, thank you. Okay, I mean, he's on the show. Okay? He's actually explaining stuff there. I mean, I think he was taking over from. I'm losing his name now. Anyway, so if you haven't seen that series, please see it. I mean, if you're in science, if you haven't seen Cosmos, I mean, I'm kind of surprised. Okay, so we talk about in the TV show, they talk about how they discover the age of the universe and stuff, age of the earth and stuff like that. Okay, and that involves mass spectrometry. But anyway, I won't talk too much. If you get a chance, I will recommend that you watch the show. But I know that you have K-pop to watch, right? Anyway, to like that. All right. So mass spectrometry, how it works. So we take the sample. We need a gas sample of that. So what we do is we take the sample and vaporize it. That's the first thing we do. After vaporizing, we make ions of the particles. And when we have ions, those ions can be accelerated through a magnetic field. Okay? And then when it goes through a magnetic field, those ions separate by their mass. And at the end, it's going to spit out a spectrum that looks something like this. I need a better color for this. So we have, that is crooked. I'm going to try a different one. Okay. So we have the y-axis, we have the x-axis. On the y-axis, we have the relative intensity. I'm going to call it REL, INT for intensity, which we do not care that much about. Okay. But the more important thing on the spectrum is the x-axis, which tells you the mass to charge ratio. So it is M divided by Z. Sometimes you might say the same thing, M divided by Q. Okay. So here M is the mass. Okay. And then charge is denoted by Z. or Q. Okay. So it can be the Q or Z. That's the idea there. Now, based on the masses of the particle, we are going to see peaks. Say that we have a particle that has a mass of 30. We are going to see a peak. Let me have a different color for the peak. Okay, we're gonna see a peak, and then that will uh, have a mass of 30. So, okay, at 30, we're going to see a peak, telling us that we have a particle that has a mass of 30. If you have another particle, I mean, it could be something like this, okay? We have another peak. So let's say that this is a particle with a mass of 70. We're going to see a peak at 70. Now, the good thing for us is this charge Z or Q is always plus 1 for our intents and purposes. For Allchem 151, it's plus 1. I mean, it's not always the case. It can change. Okay, it will be differing. I mean, if you when you take advanced classes, but for now we are going to assume that not assume. So for always for 151, Z or Q will be plus 1. All right. I will not ask you how the mass spectrometry work, but I will ask you to interpret the mass spectra, which is what the result of a mass spectrometry, which is the thing which you're seeing over there, that graph. All right. What questions, concerns, comments do we have at this moment? Anything that I can clarify? Okay. Do you have a question? No. Okay. All right. If that is the case, now we have an idea about what mass spectrometry is, how it works. Now what we're going to do is we're going to talk a little bit about it. Now you see that for this technique to work, we need to be able to produce ions. Can somebody tell me what is meant by ions? Who didn't read this entirely? What is meant by ions? What are ions? Yeah, thank you. Charged particles. Okay, if you have read that, the first point there, it actually within parentheses it tells you those are charged particles. Okay, so ions means we have a charge in those particles. That's the idea. Now, meaning if we can produce charged particles, we need to have some subatomic particles within the particle that has charges. Okay. So my next question is, okay, do we know any subatomic particles? Sub means within the atom, okay? That's the idea there. So let's try this. Out of these particles, which ones would you consider as sub? All right. We have more than 90% responses now. Therefore, I'm going to close this question in 5, 4, 3, 2. We're going to reopen that. Okay. And 1. Okay. So we have more than. All right. So here are our answers. Okay. So most of us know that the subatomic particles are electrons, protons, neutrons. I'm going to reopen them, Lucas. Don't worry about it. Okay. After class. Yeah. Okay. So, yeah, now if you pick water particles, so neon, please know that water particle contains more than one atom in it. Okay, so it's not water particles cannot be found within atoms, and neon itself is a type of atom. Okay, it is not a subatomic particle. So subatomic particles are particles that can be found within an atom, like neutrons, protons, and electrons. Do we have any questions, concerns, comments about this? Okay. So now that we know the subatomic particles, let me reopen this now so that Lucas can answer that too. Okay. So Lucas, here we go. I'm going to reopen it. Okay. Now let's think about the electrical nature of these particles. Okay. So when it comes to the neutrons and protons, does anybody know where we can find them within an atom? Where do we find neutrons and protons in an atom? Thank you. I heard that. Yes. Right? And where do we find the electrons? Yeah, around it. Okay. Or we also call this electron cloud. Okay. Now, I'm going to point out two things here. Even though we call it an electron cloud, please don't be mistaken. There's no clouds around the atom. Okay. So the idea is electrons are so tiny, and and it also moves around all the time. We cannot pinpoint the location of an electron at a given time. This is also known as the Heisenberg uncertainty principle. Okay. So what scientists do is, instead of trying to pinpoint where the electron is at a given time, they define a region in space where we can find the electron. And that seems like a cloud around the nucleus, and that's why we call that the electron cloud. Okay? So please keep that in mind. And then the other thing I want to point out here is the size. If you compare the atom to a football stadium, the nucleus is like the football at the center of the football stadium. The rest of the space is determined by the electron cloud, meaning empty space. Okay, so we are made of atoms. In other words, you and me are empty, right? So if you think about it. Anyway, so what questions, concerns, comments do we have at this moment? Anything? This is just to acknowledge a few things that we might already know, or maybe not know, but we need to appreciate that. Any questions, concerns, comments at this moment? Okay, so only things I mentioned is neutrons and protons are found in the nucleus, and electrons are around that in electron cloud. And then size of the atom is mainly determined by the electron cloud. The nucleus is so tiny, which is going to be located at the center of the atom. That's all we have, established so far. Okay. All right. So with that, let's think about this slide kind of spoils it, but that's okay. One charge. Okay. That's what the bartender told the neutron when he asked how much for the drink. For you, no charge. All right. Anyway. And then electrons are negatively charged, and then protons are positively charged. Okay. Do we have any questions about this? If you had a different answer, I'll reopen this as well. But we need to understand that neutrons are neutral, and then electrons are negative, and protons are positive. I just want you to have that basic idea. Any questions, concerns, comments? Okay. Now let's consider this. So the idea is the charge. So by the way, number of protons of an atom, okay, you should be able to tell me the number of protons an atom has, okay, for any given element, okay, using the periodic table. How do we do this? You go to the periodic table, you should be able to see a whole number next to the symbol of the atom. For example, for hydrogen, it is 1. Okay? And that 1, the number 1 is known as the atomic number of hydrogen. And that also tells you the number of protons it has. Okay? And if you go to helium, it should have number 2, meaning it has 2 protons. If you go to lithium, it has number 3, meaning it has 3 protons. So the number of protons are going to determine the number of proton is going to determine the identity of the element. You cannot change the number of protons of an element and call it the same name. For example, if you take lithium, which has 3 protons, and if we add 2 protons to that, okay, it is not lithium anymore. Okay, it is going to be boron, so which has 5 protons. Okay, So changing the number of protons will change the identity. So don't do that. They don't like it. Okay? So as chemists, we only play with the electrons, more specifically valence shell electrons, but let's get that a little bit later. But that's what we're doing in chemistry. And if you are interested in changing the number of protons and stuff like that, that has to do with nuclear physics. Okay? It's a different story. All right. So any questions so far about the atomic number and the number of protons? Atomic number is same as the number of protons. And where do I find them? From the periodic table. Okay. All right. Can somebody tell everybody, can you write the atomic number of sulfur and the number of protons it has? Go ahead. You guys have a whiteboard? Okay, wonderful. All right. Can I see a whiteboard? Can you raise your whiteboards, please? I want to see. All right. I see. Everybody, I want to see your whiteboards. 16, 16, 16, 16. Yes? Yeah? So we know how to find the number of protons of an element. Okay? All right. We are leveling up. Very good. So the other thing I want to mention here is the charge of the electron. Now, let me backtrack. The charge magnitude of the electron and the proton are the same. They have opposite charges, but they have the same charge magnitude. Okay? So if you have a neutral atom, meaning the net charge of the atom is 0, then the number of electrons it has should be same as, anybody? Thank you. The number of protons it has. Okay. If they differ, then you got yourself a charged atom, or we call the ion. Okay. So one more time, in neutral atoms or particles or molecules, anything neutral, anything. Okay. The number of electrons is same as the number of protons. Okay. The idea is they have the same charge magnitude, but opposite charges. For it to be neutral, the number of protons and number of electrons must be the same. Yeah. So if you know the number of protons from the atomic number, you also know the number of electrons it has now as well. Yeah. So we know how to find the number of protons and the number of electrons an atom has now based on that. Okay. And then I will not talk about the neutrons for the moment because it's going to change. Okay. We'll talk about that a little bit later. All right. Only other thing I want to mention from this slide is the mass of the electron is so tiny. Okay. So it's actually almost 1/2000th of the mass of a proton or a neutron. Or in other words, the mass of a proton or a neutron is 2000 times the mass of an electron. Okay. The idea is electrons are so light compared to a proton or a neutron. That's it. All right. Any questions, concerns, comments at this moment? We'll get into the implications of this in a second. Okay. So let's do this. Let's try to do this problem. If a certain positively charged ion contains 10 protons, how many electrons does it likely contain? And as a bonus activity, write the identity of this element on your whiteboards. Yeah. I want you to write the identity of this element on your whiteboard as well. All right, we have more than 90% responses now. Therefore, I'm going to close this question in 5, 4, 3, 2, and 1. By the way, what is it? Can you raise the whiteboards, please? I want to say it. Yeah, it's neon. Yeah, exactly. Okay, it cannot be anything else. It has to be neon. Why? Neon is the only element in the periodic table that has only 10 protons. Okay, if it is 10 protons, it cannot be anything else than neon. Okay, all right. And then the charge, the number of electrons. Here are our responses. Most of us picked option C, and that's the correct answer as well. Anybody who picked 10, so the idea is it is positively charged, right? So let's say this is my number of protons and number of electrons. We know this is 10. This is 10 and this is 10. Number of electrons, 10, 11, and 9, right? So if we have 10 protons and 10 electrons, the net charge must be what? Net charge should be 0. Okay? If we have 10 protons and 11 electrons, the net charge must be negative because you have more negative particles in the atom. Electrons are negative. Okay? And if you have 10 protons and only 9 electrons, the charge must be plus 1. Why? You have less negative particles than the positive particles in the atom. Okay, that's why option C is the correct answer. Any questions, concerns, comments at this point? Okay, so that is about the charged particles. By the way, whenever we produce charged particles, we only play with the number of electrons. Why? If we start playing with number of electrons, we are playing nuclear physicists, not chemists. Okay, so we are not going to do that. Okay, and because we are changing the identity of the elements if you do that. All right. Anyway, just a side note there. All right, let's try this. The relative atomic mass is the other number you have in the periodic table next to the atomic number. Okay. For neon, apart from 10, you should see another number which read like 20.18. Okay. That's the relative mass or relative atomic mass of neon. And we have talked about this last week. All right. Do not overthink this. I'll give you 15 more seconds to submit your answers. All right. I'll reopen the question, but not until after I talk about this. Okay. So here's a question for you. So I weigh 138 pounds. I checked this morning, so it is accurate. Okay. All right. So let's say that I weigh 138 pounds with a pocket in my, with a pen in my pocket. Okay. And I remove my pen and weigh again. What will be my weight? Still 138. Same thing goes here. When we produce neon plus, what do? We remove an electron, which is negligible compared to the mass of the entire atom. Okay, so therefore, removing or adding electrons will not change their mass. Okay, and then the answer for this question is still 20.18. And that's why we produce ions by, adding or removing electrons, okay, not by playing with the number of protons. All right. Any questions, concerns, comments at this point? I'll reopen this as well. Any questions, concerns, comments? Anything? All right. If that is the case, let's do this. Now let's play analytical chemist now, okay? Let's say that you are producing a mass spectrum for neon. You are doing mass spectrometry on neon, sample of neon, okay? What I want you to do is I want you to draw the mass spectrum of neon, which is what is coming out from the mass spectrometer if you use neon as a sample with your mass spectrometer. Go ahead. And I want to see the number for your peak. Please label the axis, and also for each peak, I want you to, if you have more than one peak, okay? If you have the peak, make sure that you write the number that is corresponding to that peak on the x-axis. All right. Please get used to writing the axis labels when you are drawing graphs. It's really important that you do that, okay? So we have mass to charge ratio here, okay? If I were you, I think most of you did that, but some of you had a little bit more information than the others. It's okay. So according to the periodic table, neon has a mass of 20.18, meaning if you do mass spectrometry on neon, you see a peak, one peak at 20.18. This is what I would draw. And this is what most of you drew as well. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns? Yes. We have a question over there, Carlos. You have to remind me your names one more time.
Pierce.
Yes.
So what is the graph? I don't really know what's going on.
Give a little bit more information.
What is the graph?
So this is what the mass spectrum spits out. So we have a particle that has a mass of 20.18, right? So for that, we see one peak there, which has a mass of 20.18. That's it.
What is the y-axis?
Oh, relative intensity. We don't care about that, too much.
Okay.
At least for the moment.
Okay.
We only care about, we see a peak at 20.18 because we have a particle that has a mass of 20.18. That is it. That's all the mass spectra does.
Okay, cool.
All right. Any other questions, concerns, comments at this moment? Okay. Now, here's the thing though. Now, this is what we expect based on what we know. However, when we actually did the experiment, we did not get a peak at 20.18. So here are my neon particles. Okay. I'm going to ionize them by, using an electric field. And then I'm sending it through a magnetic field, and it's going to separate by their weight. And that gave us, the spit out, a mass spectrum that had 3 peaks, not 1, 3 peaks. This is not what we expected based on the periodic table. We had 20.18 particles according to the periodic table. But in actual experiment, we got 3 peaks. Any idea? Why do we have 3 peaks now? Not 1 by 3 peaks. Yes, sir. Carlos? Let's see. Remember your name, sir?
Isaac?
Isaac, go ahead.
Because there's different isotopes of neon.
Tell me more. What is that?
So an isotope is like, it has the same number of protons because they're all neon, but the numbers of neutrons vary.
Okay, exactly. So we got 3 peaks here because they have different isotopes. So I'm going to elaborate on that. So let's see if I can do this. I'll try to switch to my notebook. Okay. All right. So we did the experiment. We were expecting one peak, but we got three. And then those peaks were, let's say, relative intensity. And this is the mass to charge ratio. We got three peaks. We had one at, I forgot already. Okay. We had one around at 20. I'm going to draw them. We got one at 20. Okay. Let's say this is 20. And then we have another small peak at 21. And then another peak at around 22. So the relative abundance or relative intensities of these peaks are 90.48% for 20 and 0.27% for 21 and then 9.25% for 22. I'm going to expand this. This is what we got. Okay. Now, how do we explain this? We know these are neon. So the number of protons must be what? They should all have how many protons? Everybody. 10 protons. Thank you. 10. Because that's the identity, because this is neon. Okay. So if we have neon 20, what can you tell me about the number of neutrons it should have? Any ideas? Any guesses? So make it 20. How many neutrons should it have? 10. Thank you. So neon 20 isotope has 10 neutrons. What about neon 21? How many neutrons should it have? 11. And what about neon 22? It should have 12. Okay. So they have the same number of protons, but different numbers of neutrons. And these are known as different isotopes of neon. Okay. So the isotopes are, presented in different ways. You can either use the atomic symbol. In atomic symbol, we have the symbol for the element and the number of protons here and the total of protons and neutrons at the top left corner like this. Okay. And this is also known as the mass number. This is also known as the mass number, while this is the atomic number. The atomic number. All right, I'll do the other one as well. For neon 21, okay, we have 10 protons, but the mass number, which is protons plus neutrons, is 21. And then neon 22, this is 10, this is 22. Okay, so the mass number is number of protons plus number of neutrons, just for bookkeeping purposes. These are known as the atomic symbols of the isotopes. Okay, and you can also see that these isotopes are presented like for neon 20 like this, neon 21, neon 22. They mean the same thing. Okay, so those are other ways of these isotopes can be presented to us. Any questions, concerns, comments at this moment? Anything? Now, here's the big question though, okay? Your periodic table tells you the relative mass of neon is 20.18, okay? None of these peaks are at 20.18. So what is 20.18 then? Does anybody know? I heard that. What is that? Yeah, that's the average relative atomic mass. So what do we mean by that? Okay, actually that's the weighted average. So it goes like this. So you see that from neon 20 isotope, you have 90.48%. So if you take 100 atoms of neon, okay, 90.48 48 out of that 100 will have a mass of 20. To that, I'm going to add neon 21. If you take 100 atoms of neon, 0.27 will have a mass of 21. Yeah. And if you take 22, neon 22, if you take 100 atoms of neon, 9.25 of them will have a mass of 22. Can somebody plug these numbers into a calculator and let me know the answer? What do you get? Everybody should do this. Okay. Take out the calculator because you will be doing this on your own in homework assignments, in quizzes, and stuff like that. So, all right. Can somebody tell me what you got? What did you get? Anybody? 20.1. Okay, 20.18 or 19? 18, isn't it 187? Yeah, that should be 19. Yeah, I would say it's 20.19 or 187. Okay, so you get 20.187 mu. Okay, and this is what you should see in your periodic table. Now, wait a minute. Aren't we seeing 20.18? But we got 20.19. Does anybody know what's going on there? Anybody? So we should get 20.18, right? That's what the periodic table has. But we have 20.19. Okay, by the way, this is called the average relative atomic mass. This is how we find the average relative atomic mass. Okay. Now, let me explain the 20.1819 conundrum here. Okay. The idea is this. So the actual mass of neon 20 isotope is not 20, it's 19.99. Okay. And the neon 21 is not 21, it's 20.99. And the neon 22 is 21.99. Even though we are combining one neutron with another proton, which has the same mass, okay? Even we still get a lesser mass than the sum of those two. Okay, that's why as the average relative atomic mass, we get 20.18, not 20.19. Now, this is the beautiful thing, actually. Okay, does anybody know why we do not get 20? Let's say for neon 20 isotope, why do we have 19.99 instead of 20 when you had one proton with one neutron? Anybody? The neutrons and protons have the same mass. If you add 10 protons to 10 neutrons, it should be 20, not 19.99. But why is it 19.99? This has to do with Einstein. E equals mc squared. The idea is some of the mass is converted to energy. Therefore, we lose that mass. It's binding energy, as binding energy. And that's why it is not 20, it is little bit less than 20, 19.99. Okay, this is a little bit beyond 151 for this part, but I think it's an interesting thing to make note of. Okay. Anyway, so if you had these numbers, you will get 20.18, exactly 20.18 if you use the exact numbers given to you. Yeah. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? Okay. If that is the case, I'm going to, I don't have any doodling. It's great. We talked about the atomic symbols, the atomic number and the mass number, and then we talked about this as well. So with that, Let's try this question one more time. This is the first question I opened at the beginning of the class. Can you find the average relative mass of X? And also identify X as well, okay? So we definitely have more than 90% responses now. Therefore, I'm going to close this question in 5, 4, 3, 2, and 1. All right. And here are our responses. Beautiful, okay? Most of us said the answer is, you know what, let me do this. Okay? So we have two isotopes. By the way, we have two isotopes. How do we know two isotopes? Because we see two peaks here. Okay? So we have isotope 10 and isotope 11. Okay? So X10 and X11, that's what we have there. So for 10, if you take 100 particles of X, 20 of them will have a mass of 10. Okay? And then we have 11. If you take 100 particles of this, 80 of them will have a mass of 11. That's what it means. So if you, I don't have a calculator, so I'm going to do it over here. So this is going to be 2 plus, and this part is going to be, I think, 8.8. 8.8 together, this is going to give us 10.8. So that's the average relative mass of this substance over here. And then we take this to the periodic table and see which substance has the average relative mass of 10.8. Which is it? Everybody. Thank you, boron. Boron is the element with the average relative atomic mass of 10.8. That's it. We achieved the learning objective for today. All right. What questions, concerns, comments do we have? Yeah, do you have a question, sir? No? Any questions, concerns, comments? Anything that I can try to clarify? Are you okay with this? Do you have a question? Yeah. Okay, wonderful. All right. So that is that. Now, all this time, we did mass spectrometry of atoms. Like, just one atom, neon, argon, okay? It's kind of boring in a way. Okay, even though it's interesting in its own right, but compared to molecules, it's boring. Okay? So think about the molecule is, the molecules break apart under the harsh conditions of mass spectrometry. As a result of that, we get fragments of the molecules. Okay? And then when those fragments will have different masses. I'll give you an example. Okay? So if you do mass spectrometry on CH4, which is a molecule, you're not going to see just one peak at 16 for its relative mass, because carbon is 12, hydrogen is 1, we have 4 of them. 12 plus 4 is 16. We expect a peak at 16, right? We get more than that. We get a peak at 15, 14, 13, and 12, and so forth. Okay? Now, you don't write down anything yet. Okay, I'm going to come back to this. Now, I have an analogy here. Okay? So, let's say that I have a box of ornaments. Okay? And that ornament is made of a pyramid, a sphere, and a cube. You know what? Let's forget about the pyramid. A triangle, circle, and a square. Okay? So I have a box that contains 100 of these ornaments. Okay? So I'm gonna give this box to a person from ASU. You know what's gonna happen, right? Right? That they're gonna drop my box. It's almost certain they're gonna drop my box. Okay? So when they drop my box, what's gonna happen? Some of my ornaments break into pieces. They fragment. Without saying break, let's say fragment now. It's a different word, yeah? fragment into pieces. Okay. Now, when they fragment, they break at the places where they are glued in. So my ornament is glued between the triangle and the circle and the square. Okay. And that's how they break. Okay. So they're going to break at those points where we have glued them together. Okay. Now, here's the question for you. If you did mass spectrometry on this, how many peaks do you expect? And can you draw them for me? Go ahead. I see 20, 30, 40. Okay. Let's say. Label the axis. Actually, I understand what you drew there, but it's a good practice, especially when it comes to your lab and stuff like that, not to lose points, to label the axis of your graphs. All right. Now, okay. So here's something to remember, okay? When you're doing mass spectrometry, when you're handling mass spectrometry here, you should be able to explain the peaks. That should be one of your goals. Okay. So let's see what we have here. Most of you got at least 3 peaks. You should get maybe 50% of the points if this was an exam question. If you had 3 peaks. Now let's see what we can have here. Okay. So we said that we have a peak at 20. Okay, good. Oh, that's crooked. All right, that's it. Okay, peak at 20. Okay, why? We can have the triangles, broken off triangles, will have a mass of 20. And then we have a peak at 30. Okay, why? The circles have a mass of 30. And then we can also have a peak at 40. Okay, we peak at 40. Why? We can have the squares by themselves. Okay, and also we can have a peak at, let's say, 50. Okay, why? We can have this triangle and the circle together, but just the square is broken up. Okay. Also, we can have a peak at, say, this is 70. Yeah, we can have 70, right? This is 50. Okay. We can have a peak at 70. Okay. Why? We can have the circle and the square together. This is 70. Oh, include alert. Anyway. All right. Anyway, and also, here's the thing. Some of my ornaments will even survive an ASU person, right? Some of them. So we should get a peak at 90 as well. Okay. We should get a peak at 90. Why? That contains the intact ornament. Survivors. Okay. And therefore, thus we can come up with 6 peaks for this. All right. What questions, concerns, comments do we have at this moment? Any questions, concerns, comments, anything? We have a question over here. Remember your name, miss?
Reva.
Reva, go ahead.
So like it can't be 60 because like the triangle and the square aren't like touching.
Can it be?
So it can't be like fragmented.
Reva, your question is, can we have a peak at 60? Is that right?
Yeah.
No. We can. Anything is possible. What you're saying is, so everything is broken off and then the square and the triangle comes together. But that has to be done separately, right? Somebody has put them together for you to have that peak. Yeah, because they're not together at the moment, right?
Okay.
Yeah?
So like just decide like there won't be any peak at 60.
We cannot, because according to the way it is put together, okay, we do not have the square and the triangle together at any point. Therefore, there's, unless somebody glue them back together, you cannot have that. Yeah? Yes, we have a question here, Carlos. What's your name, miss? Edison, go ahead.
For like 50, 70, and 90, how do you know like that's how tall it is?
I don't know. I just came up. I just randomly put them there.
Okay.
Yeah. Oh, yeah. So Edison's question is, it's a valid question. How do I know how tall the peaks are? I have no idea. Okay. Yeah. So here's the thing. The height of the peak depends on, get this, the stability of the fragment. Only thing I can tell you from here is when my circle and the triangle put together, glued together, it seems to be more stable than anything else. That's all I know. Okay? So, yeah. And that's all I know based on this. Yeah, I came up with this randomly. Okay? But any other questions, concerns, comments? Okay? All right. Now, this is the same idea when we go to a molecule. Okay. So if this is our molecule, the molecule will break into pieces, and those pieces will register on the mass spectrum with their corresponding masses. That's it. Okay. Now here's the next. I'm not going to delete this because I think. Oh, no. Can I go back? I'm sorry. All right, let me call this. Okay, so I'm going to call these peaks A, B, C, D, E, and F. That's a song like that, right? A, B, C, D, E. Right, anyway. All right, anyway. Not the alphabet song. I mean, there's another song. Anyway, that reminded me of that. Anyway, here's the question for you. On your whiteboards, I want you to tell me which peak out of all these peaks can tell me the mass of the entire ornament. Go ahead. Which peak can tell me the mass of the entire ornament? I'll give you 10 seconds. Don't tell me the answer yet. All right. All right. Can I see your whiteboards? Which peak tells me the mass of the entire ornament? Don't overthink this. Just look at the what you drew. Anybody from here? What you guys said? Okay? Okay? Do we have a whiteboard there, Ryan? Perfect. Thank you. Thank you, sir. All right. All right. So, yeah. Almost everybody, okay, told me that this peak over here, let me have pink for that, okay? This peak over here tells me the mass of the entire ornament, okay? This peak over here, which is the peak corresponding to the highest mass, not the tallest, the highest mass, okay, is known as the molecular ion peak. This is known as the molecular ion, I like pink, molecular ion peak. Okay, and that tells you the mass of the entire ornament or entire molecule if it was a molecule. Okay, one more time. Okay, it is not about the height, it's about the mass. Okay, I've told this several times in class. Okay, height doesn't matter. Okay, I'm biased, of course. Anyway, it doesn't matter. All right. Anyway, anyway, what questions, concerns, 90% responses. I'm going to close this question in 5, 4, 3, 2, and 1. And here are our responses. Okay. So most of us picked option C, and that's the correct answer as well. Again, anybody who selected B, the height does not matter. Okay. Okay. What matters is the peak that corresponds to the highest mass, and that gives you the mass of the entire molecule, and that is the molecular ion peak, and that tells you the molar mass of the compound. All right. So based on this, I can see that we have 1, 2, 3, 4, 5. So that means each tick mark is 2. So our peak C is at 32. So the molar mass of this compound relative mass of this compound must be 32. If you take the gram amount of that, that will contain 1 mole of this molecule. Therefore, molar mass is 32 grams per mole. All right. What questions, concerns, comments do we have at this moment? Any questions, concerns, comments? Okay. So here's the last thing I want you to do, I think. Oh, by the way, nobody asked, but I think I should mention this anyway. So this is CH4. We know the molar mass of this is 16. So here's the peak for 16. It happens to be the tallest peak as well. Okay, that's okay. All right. Sometimes it happens, not all the time though. So the idea is you get a peak at 15. Why? If you break one hydrogen, no. If it fragments by, so here's CH4, by the way. Here's CH4. Okay. So for that, I'm going to get the peak at 16. And then if one of these hydrogens breaks, let's say that we break it from here, then we're going to get CH3. So for that, we're going to get a peak at 15. And then 2 of them breaks, we're going to get a peak at 14 and peak at 13. And then if all the hydrogens break off, then I'm going to get a peak at 12 just for carbon. That's the idea there. Okay. And I included the plus sign here. The reason is without the charge, the mass spectrum cannot register it. We need the charge for it to go through the mass spectrometer. Okay, that's why I include the charge, but it's not that significant because it's always plus 1. And the other thing is, you might have noticed, or maybe not, I don't know. Okay, depending on who you are. You see a very small peak here. Okay. This peak is still a molecular ion peak, but with another isotope of carbon. There's another isotope of carbon called carbon-13 isotope, which is a little bit heavier. Okay. But only about 1% or less. I can remember the exact percentage now of carbons are carbon-13. So therefore, we get a very small peak like that, usually with the carbon-containing compound, just after the usual molecular ion peak. But by the way, okay, that is also a molecular ion peak with the different isotope. Okay, so if you use that for something we're going to be doing on Thursday when we're determining the composition of the molecule, you should still be fine. Okay, if you're being one point off, it will not make a big difference. I mean, I'll prove that to you on Thursday. Okay. All right. So with that, last thing as a take-home message. All right. I know that we are getting ready to leave. I understand that. Okay, I know. But anyway, I have at least 2 more minutes. Can you at least identify 2 of those main peaks? This is the molecule given to you, CH3OH. Okay. Can you identify at least 2 of the other peaks apart from the molecular ion peak? For an example, this is this molecule fragment. This is the entire molecule. Right? Okay. I'll do this one, the tallest peak. The tallest peak must be due to breaking the molecule from one of these hydrogens. If you do that, I'm going to get CO, H, H, H plus. And I'll do one more actually. That's okay. I'll do this one. Can you draw, last thing, I promise. Can you draw the molecular fragment corresponding to 15? Then we're done. 15 on your whiteboards, please. What is this fragment due to? The peak due to? Which fragment? Does anybody have it? Anybody? Thank you. Wonderful. So that would be 12. We need 3 more. We need that 3 more. All right. So that should be due to CH3.